After studying this module, you shall be able to know what is one-way ANOVA, learn to identify situations for application of one-way ANOVA, evaluate and analyze one-way ANOVA variables, hypothesis and theoretical process behind it. Know the meaning of F statistic, learn to apply the technique of ANOVA in reality and identify the application areas of ANOVA. Working of ANOVA on your own and analyze its results. Many companies in the market are selling milk powders for children to facilitate their growth and claiming to enhance their intelligence. The consumer, especially the parents, are confused as to which of the brands would be the best for their child. The brand that should be chosen can be inferred by doing a research that compares the effects of those brands on the physical and mental growth of the children. Had there been just two competing brands, we could have used a t-test and compared their effects. When it comes to comparing the effects of more than two brands of milk powders, ANOVA would be more useful. What is ANOVA? The statistical model that helps to analyze situations in which one wants to compare more than two conditions is the analysis of variance model, or the technique called ANOVA in short. This procedure is used for testing the hypothesis that K population means are equal where K is greater than or equal to 2. One-way ANOVA compares the means of the samples or groups so as to make inferences about the population means. It is also called the single factor analysis of variance, since there is only one independent variable or factor. The independent variable may have nominal levels or a few ordered levels. For instance, as depicted in the picture, one can compare the performance of three candidates representing three different political parties during their canvassing before elections in their ability to generate their vote banks. Need for ANOVA. If there were three experimental conditions, for instance, the consumer responds to three different types of ketchups and one was interested in finding differences between these three conditions, one would have to carry out t-test on every pair of groups, one to compare groups 1 and 2, one to compare groups 2 and 3 and another one to compare groups 1 and 3. If each of these t-tests uses a 0.05 level of significance, then for each test the probability of falsely rejecting the null hypothesis is also referred to as type 1 error. Thus, the probability of no type 1 error is 0.95 for each test. If each test is assumed to be independent, then the overall probability of no type 1 error is 0.95 into 0.95 into 0.95 equal to 0.857. Because the probability of no type 1 error is 0.95 for each test and there are 3 tests, since the probability of no type 1 error is 0.857, one can calculate the probability of making at least one type 1 error by subtracting this number 1, which equals 0.143 or 14.3%, a value greater than the criteria accepted by social scientists. This error rate across statistical tests conducted on the same experimental data is called experiment-wise error rate. If the number of experimental conditions keep increasing, then the number of t-tests required would increase as well. consequently increasing the experiment-wise error. Experiment-wise error is equal to 1 minus 0.95 to the power n. Therefore, ANOVA comes to the rescue. Instead of conducting several t-tests, we have just one test, that is analysis of variance. The components of ANOVA. Variables in one-way ANOVA. There are two types of variables in one-way ANOVA. Independent variable. It is the controlled or manipulated variable that is controlled by the researcher. It is a categorical or discrete variable used to form groupings or observations. One-way ANOVA considers only one independent variable which can have two or more than two levels. Independent variables, also referred to as a factor, divides the individuals into two or more groups or levels. Independent variables can in turn be of two or more subtypes. Active variable. An active variable is such a variable in which the values can be manipulated to study its effect on another variable. For instance, anxiety level or the fatigue levels. Attribute variable is such a variable where one does not alter the variable during the study. For instance, studying the effect of age on weight. One cannot change an individual's age, but can study people of different ages and weight. The other variable is the dependent variable. It is a continuous variable presumed to result from manipulation of independent variable. In one-way ANOVA, there is just one dependent variable and hypotheses are formulated about means of groups on that dependent variable. This dependent variable differentiates individuals on some quantitative or continuous dimension. ANOVA F test evaluates whether group means on dependent variable differ significantly from each other. An overall ANOVA test is conducted to assess whether means on a dependent variable are significantly different among the groups. Models of ANOVA. One can choose the levels of independent variables by selecting them deliberately, or one could sample them at random. Fixed model. If levels of independent variable are selected because they are of interest or all the possible variables, it is a fixed model. The levels do not constitute random samples from some larger population levels. Treatment levels are selected intentionally and remain constant from one replication to another. One can generalize to only the levels tested with the help of this model. Random model. If the levels of independent variable are randomly selected from a larger population of levels, it is a random model. The treatment levels are selected randomly, and on replicating the study, one could choose the levels randomly and is most likely to have a new set of levels. Thus, the results using this model can be generalized to population levels from which the levels of independent variables were randomly selected. Hypothesis for one-way ANOVA. Null hypothesis HO. Population means from which the K samples are selected are equal or each of the group means is equal. That is, HO is equal to mu1 equal to mu2 till the mu k, where k is the number of levels of independent variable. Alternative hypothesis HA is at least one group mean significantly differs from other group means, or at least two of the group means are significantly different. HA can be mu1 is not equal to mu k. Mu I is not equal to mu k, where I and k indicate unique groups. Formulae in one-way ANOVA. ANOVA partitions total variability of data, that is SST, into two sources. variability that exists within each group called within group sum of squares, and the variability that exists between groups called the between group sum of squares or SSB. Each sum of squares is used to form an independent estimate of HO population variance. The estimates based on within group variability is called within group variance estimate, also called as MSW, and the estimate based on between group variability is called between group variance estimate or MSB. Thereafter, an F ratio or F obtained is calculated, where F obtained is equal to the mean sum of square of between groups upon the mean sum of square of within groups. The mean sum of square within reflects differences between among the subjects exposed to same treatment. This variation within any one group is a function of specific subjects selected at random for the group or allocated at random to the group. This variation can be attributed to a random sampling fluctuation, that is sampling error. The mean sum of square between reflects differences among group means. Even if there were absolutely no treatment effects, it would be unlikely that a sample mean for groups would be identical. One would expect group means to vary due to random selection process in formation of groups. Thus, this variation reflects variation due to treatment as well as variation attributable to random process by which subjects are selected and assigned group. Therefore, the F is equal to treatment effect plus error upon error. When the null hypothesis is true, that is, there is no difference between group means or no treatment effect, one would expect F to be equal to 1. Larger the F ratio, the more reasonable it is that the independent variable has had a reasonable effect or a real effect. If the F ratio is less than 1, the treatment has had no significant effect. The summary of ANOVA. The summary of ANOVA table is given at the end of ANOVA, which contains the source, sum of square, degree of freedom, variance estimate or the mean squares, and the F ratio. The graphical representation of the ANOVA distribution is also shown here. When the null hypothesis gets rejected in ANOVA, it implies that there are significant differences among sample means than would be expected due to chance. A measure of strength of association between independent variable and dependent variable in ANOVA is omega squared. It indicates the proportion of total variance in dependent variable that is accounted for by the levels of independent variable. In omega square of 0.4135 means that the independent variable in ANOVA accounts for approximately 41.35% of total variance in dependent variable. Of course, we will take up numericals and we will see how this is found. Assumptions for one-way ANOVA. One-way ANOVA assumes that assumption of independence, that is, the observations are random and independent samples from the population are chosen. Null hypothesis assumes that samples come from populations having same means. Samples must be random and independent if they are to be representative of other populations. Value of one observation is not related to any other observation. It implies that one person's score should not provide any clue to how any of the other people should score. That is, one event does not depend on the other one. Assumption of normality, that is, distributions of populations from which samples are selected are normal. It implies that dependent variable is normally distributed in each of the group. Assumption of homogeneity of variance, that is, variances of the distributions in the population are equal. It implies that the distributions in the populations have the same shapes, means and variances, or are the same populations, or the variances on dependent variable are equal across the group. A company desires to compare 4 programs for training workers to perform a certain manual task. 20 new employees are randomly selected and assigned to training programs. 5 employees are placed in each program, and when the training period terminates, a test is conducted to assess how quickly trainees are able to perform the assigned task. Had there been 2 programs, we could have done a t-test and inferred which program can be considered better than the other. But as there are 4 programs to be compared, ANOVA would be applied. Interpretation of F statistics. F statistics, named after Professor Ronald Fisher, is produced by ANOVA. When a test is performed, the hypothesis that 2 sample means have the same mean is tested. Similarly, ANOVA explained whether 3 or more means are the same, testing the null hypothesis that all group means are equal. F ratio is similar to T statistic, comparing the amount of systematic variance in data to amount of unsystematic variance. ANOVA test for an overall experimental effect, also called an omnibus test. Even though ANOVA tells us whether experimental manipulation is successful or not, it does not give specific information about which groups are affected. F ratio may tell us that the means of 3 samples are not equal, that is, x bar 1 equal to x bar 2 equal to x bar 3 is not true, but there are various possibilities in which the means may differ. All sample means may differ significantly, or means of group 1 and 2 are same, but group 3 has a significantly different mean from both the other groups. Similarly, group 2 and 3 may have similar means, but group 1 might be having significantly different mean, or it could be that groups 1 and 3 have similar kind of mean, but group 2 may be having significantly different mean from both. So, in an experiment, F ratio can only tell that experimental manipulation had an effect, but not specifically tell us what the effect is. For example, the transport department wants to examine the safety of compact cars, mid-sized cars and full-size cars. They collect a sample of 3 each for each of the treatment conditions, that is, the car types. If using the hypothetical data, one wants to test whether the means pressure applied to driver's head during a crash test is equal for each types of car with alpha equal to 5%. The data is compact cars, mid-size cars and full-size cars, and this is the reading for the pressure. X bar and standard deviations are calculated, and let us see what we do. First step would be stating the null and alternative hypothesis. Null hypothesis for ANOVA, as we already know, assumes population means are equal and represented as HO equal to mu1 equal to mu2 equal to mu3. This implies that the mean head pressure is statistically equal across the 3 types of cars. Thus, the alternative hypothesis would be the means not being equal, or HA is at least one mean pressure is not statistically equal. Next step is to calculate the total sum of squares using the formula. R is the number of rows in the table and C is the number of columns. X with double bar is the grand mean and Xij is the ith observation in the jth column. Based on the data given in the table above, the grand mean is calculated, sum of square for the totals is calculated, and we calculate the treatment sum of square using the formula or the between sum of squares, that is variation in the data between different samples, where Rj is the number of rows and jth treatment and x bar j is the mean of the jth treatment. Based on the data given in the table, the SSB or sum of square between is also calculated. Calculate within variation or error sum of square, that is variation in the data from each individual treatment. Based on the data given in the table, the sum of square of our errors is also calculated, and note that SST is equal to SSB plus SSE. Compute the average source of variation in data using SST, SSB and SSE, and we get mean sum of square for the total by SST divided by n minus 1, where n being the total number of observations. Mean sum of square total is also calculated, and then mean square treatment between the conditions is calculated by the average between variations, C being the number of columns in the data table. The mean sum of square for between treatment is also calculated, and mean sum of square for errors is also calculated, that is average within the variations. It is to be noted that mean sum of square total is not equal to mean sum of square between plus mean sum of square error. Calculating one-way ANOVA statistic, now being the ratio of the average between variations to the average within variations is represented as f is equal to mean sum of square between upon mean sum of square error, that is 25.17 in this case. If the average between the variation rises compared to the average within variations, f statistic will rise, and so does the chance of rejecting the null hypothesis. Now, how to obtain the critical value to check the significance? The critical value requires knowing the degrees of freedom for the numerator, that is mean sum of square between, as well as for the denominator, that is mean sum of square error, along with the significance level. F critical has df1 and df2 degrees of freedom, where df1 is the numerator degree of freedom equal to the number of columns minus 1, and df2 is the denominator degrees of freedom equal to n minus the number of columns. In the example, df1 is equal to 3 minus 1, that is 2, and df2 is equal to 9 minus 3, that is equal to 6. Hence, F critical corresponding to alpha using the F tables is found to be 5.14. Now, we may check the hypothesis. Checking the hypothesis is done by rejecting the null hypothesis if our F obtained value is greater than the F critical value which we get from the table. In the example, we know that F obtained is 25.17, which is definitely greater than 5.14, that is the critical alpha value from the table. So, we reject the null hypothesis. Next step is interpreting the results obtained. Since the null hypothesis has been rejected, considering alpha is 5% and 1 is 95% confident that the mean head pressure is not statistically equal for compact, mid-size and full-size cars. But since only one mean must be different to reject the null hypothesis, one does not know as yet which mean or means are different. Therefore, an ANOVA test will tell us that at least one mean is different, but an additional test must be conducted to determine which is different. Applications of ANOVA. ANOVA in reality can be applied at many positions. In social science researches, figuring out factors that influence people's opinions and behaviors can be done using ANOVA. In business administration, psychology, social science and natural sciences, when one wants to compare more than two groups for hypothesis testing, scientists use the ANOVA method. It can test more than one treatment, gives it an added advantage over other statistical tests and opens up many testing capabilities. It is used in procedures involving testing of pharmaceuticals, and therapies. It enables one to see how effective two different types of treatments may be and how durable they will be. It concludes how big a difference there would be between treatment conditions and if the effect is more than just by chance by reducing the possibility of type 1 error. Summary: one-way ANOVA is a statistical process to compare or understand differences between more than two means or conditions. ANOVA reduces the experiment-wise error rate to increase the accuracy of test results. ANOVA has one independent variable which might have multiple levels and one dependent variable. ANOVA in terms of F statistic assesses whether means on dependent variable are significantly different among the groups. It follows a fixed model or a random model depending on levels of independent variable, the generalizability of results. The null hypothesis assumes no difference in population means, and alternative hypothesis assumes a difference between means not accounted by chance. It can be carried out if the assumptions of normality, independence and homogeneity of variance are met. ANOVA would investigate differences between means of several populations simultaneously. It is appropriate when one has a dependent interval variable and when has two or more populations, that is, independent variable is categorical, making ANOVA a two-tailed t-test. With ANOVA, one tests that all means are equal or there is a difference. The rationale is to determine whether the variation in a set of data is attributable to random error or whether some variations can be attributed to actual differences in the means of the populations of interest. Total sum of squares can be partitioned into sum of square between and sum of square within. The total degrees of freedom partition into df between and df within. By dividing each sum of square by the corresponding degree of freedom, the mean sum of square between and mean sum of square within are determined, representing variability between different samples and sample variability within all samples respectively. Variability within samples may be due to random error alone, and variability between sample may be due to actual differences in the population means. If mean sum of square between is significantly greater than the mean sum of square within as measured by F test, then the null hypothesis of zero treatment effects must be rejected.